Hello everyone, thanks for joining our webinar today. If you have any questions during the session, please submit them using the Q&A button at the top of the interface. Those questions will be answered at the end. This webinar will be recorded and you'll receive a copy of it delivered to your email account. I hope you enjoy, and I'll now hand you over to our experts, Mirza Krak, who's the Embedded Solutions Architect at Mender, and Harald Kjølberg, who's a Product Manager at Qt Company. Over to you guys.
Thank you, Sala. So, welcome all. I guess we just get started. My name is Harald Kjølberg from the Qt Company, and we have the pleasure today to have Mirza Krak from Mender with us. So, Mender is one of our technology partners, delivering technology the Qt Company doesn't have ourselves. So today we will go through over-the-air updates together with Mender.io. So with that, Mirza, over to you.
Thank you very much, and welcome everybody. Thank you for joining this webinar today, where we will be talking about managing your Qt-based embedded Linux devices using Mender. So yeah, I'm planning on just jumping straight into it. So just a quick, for context, Mender is an end-to-end open source project to deploy over-the-air software updates for connected Linux devices. We will go into more details later on, but I just wanted to give you a quick introduction in what it is. And Mender was created based on extensive research and user tests in the embedded market, where we noticed that a lot of companies were developing homegrown solutions. Typically, they were developed on a project or product basis. And what we also saw based on this research, that the majority of these homegrown solutions were lacking in some regard, mostly because the company developing a product focuses on the product specific application, which brings value to the customers. And OTA is almost a second thought, and then you kind of end up taking some shortcuts. And what we saw in these homegrown solutions were that what they were lacking in is some like best practices on built-in security in regards to doing over-the-air software updates. They were typically developed in-house, so you kind of have had this tribal knowledge within the company that maybe it was developed by a single person. So there was no real community around the over-the-air solution or update solution. There were definitely some lack. That was definitely also lacking in regards to robustness, and maybe not able to handle all the edge cases which are present in the environment that we are in. And typically, some fleet management and management server were not developed because that's not the core. That's not part of the core product of that's being developed. But most significantly is that what we saw is that a lot of people or companies underestimated the effort to develop a homegrown solution, both in regards to developing it, but also maintaining it over time. And these are problems that we are trying to address with Mender, but we will come back to that later on. So I wanted to just quickly mention on who we are as a company. The company behind Mender is called Northern-Tech and was founded in 2008. Mender was started approximately 4 years ago based on this research that we did. We have a technology office in Oslo in Norway, but we also have offices in San Francisco. And we are a team of people focusing on fixing these highly technical and security-related problems in the IoT space. And the Mender is a product to trying to address some of the problems that exist today. And you can see also a snapshot of our existing customers. And we're also very proud of our partnership network. Very proud to be a technology partner of the Qt Company. Hopefully we can bring value to the ecosystem by providing this product or the project. We as a company have also partnered with some of the major cloud providers because Mender is an end-to-end solution where we provide a management server. So we have partnered with companies like Microsoft and Google Cloud and provided reference integrations for both Azure IoT Hub and the Cloud IoT Core. And the essence of these reference integrations is sharing device authentication and authorization between the Mender server and, for example, Azure IoT Hub. There's also a link in this slide. Hopefully you will get the slides later where you can take a look a bit more in detail of what these integrations entail. And Mender was also featured at the Microsoft IoT show, where our CTO and product manager of Mender did a presentation of the integration. So market needs for OTA updates, as the connected devices is an ever-growing field, with the explosion of IoT and embedding connected devices into things, there's a real explosion of devices that are connected to the internet. And goes without saying that if the device is connected, it means that it needs to be updated. The software needs to be updated on the device. And there are a couple of reasons. I mean, there will be bugs in the application. And once you ship your devices, you want to be able to remotely resolve these problems. And in some cases, bugs can become vulnerabilities. So you can get the security vulnerabilities because there's something wrong in the code. And generally, I mean, an embedded device runs millions of lines of code. So there's no way of avoiding. And there will be bugs and vulnerabilities in the code, and you need a way to update the software to reduce the risk included by this. Another value add or a competitive edge that you can have if you have built-in over-the-air updates into your product or device is that you can add new features once the devices are deployed to the field. This can significantly reduce your time to market. So you can ship the devices with the minimum bare functionality and then keep adding new functionality over time as development teams are working on it. And you also avoid recalls if there are bugs and so on. So once devices are in field, you can always update them over there to fix the problems that are found over time. And over-the-air updates are, for another reason, the embedded connected devices have lately become a large, have become popular to be for malware, different type of malware, such as Mirai or Jammerbrickebot, which are specifically targeting unsecure devices connected to the internet. And over time, as a product life cycle is typically can be 5 to 10 years. Over time, if the software is not updated in the device, it will have known security vulnerabilities. And this is what these botnets or malware are trying to exploit to get access to your device and then do various things with it. For example, Mirai was used to do a denial of service attacks where they were able to gather hundreds of thousands of devices and then utilize them to do a denial of service attacks on various sites. So it's a growing problem, and OTA can help keeping the software up to date, preventing known security vulnerabilities. So I wanted to talk a bit about the embedded environment and some of the key things which complicates over-the-air software updates. Typically, when you build an embedded device, you build it into a product and then you ship the product. And the product can be embedded in a car, or it can be, in the extreme cases, it can be underwater or on top of the mountain. So it's very expensive to reach the devices physically. So you want to be able to handle everything remotely, both failures, but also deployment of software and so on. The long expected lifetime, which is typically 5 to 10 years, imposes some challenges, specifically around keeping software up to date. Is a requirement if security is of concern. In some cases, you have unreliable power. So at any given time, the devices can be disconnected from power, and the system needs to be designed to be able to handle this. And in some cases, they're also powered by a battery, which can deplete at any given time. So there needs to be mechanisms to handle this safely. And typically, embedded devices are also connected over a mobile network or Wi-Fi, which can be of a various quality. So there will be intermittent connectivity, low bandwidth, and so on. So this imposes some challenges that needs to be handled as well. And knowing these key factors of the embedded environment, if you take a look at a generic requirement list to be able to do over-the-air updates for such devices, you would want to be able to update all the components of the system. So if your system has if it's an embedded Linux system, you want to update your application, the Linux kernel, and all the low-level system components that are built into your device. It's generally unsafe to update the bootloader because it requires hardware workarounds to build in fail-safe mechanisms. So that's something that can be done, but it's application specific. So never render the device unusable. So if you deploy a software update, no matter what happens, the device should not be bricked or unusable. So if you lose power while you are doing over-the-air software update, the device should always roll back to our previous working state. So you need to have fail-safe mechanisms in place, because it will, whatever can happen will happen typically. So this needs to be considered when designing OTA solution. You want the updates to be atomic. An atomic update means that you either installed successfully or failed. There is no in-between state. So there is no 50% successful, which can leave your system in inconsistent states, or if you have a fleet of hundreds or thousands of devices, you want it to be updated or not updated, nothing in between. And this is typically the problem with the desktop style updaters like apt-get. They are generally not atomic, and that's why they are not really suited for the embedded environment, which has different requirements compared to a PC or a server. Rollback recovery, which kind of relates to the never render the device unusable. So you want the device to always be able to recover from failures, no matter what happens. If you lose network connectivity or power, you want some built-in integrity checks. So if you transfer a firmware update from a server to a device, you want to make sure that all the bytes arrived and were written correctly on the storage medium. You want to be able to sign your firmware updates, meaning that the devices can verify the source of the updates, so they are coming from a trusted source, that is you, so to say. And you also would like to have some kind of built-in compatibility checks, and this means that certain firmware packages are only allowed to be installed on specific devices. So, and this is to avoid accidentally deploying the wrong image to the wrong device and kind of rendering it unusable or something like that. And these are things that are hard to get right, and it's been shown and it's gotten some media attention. There are a couple of companies that are doing over-the-air software updates for a while now. For example, Tesla is a good example of where they have been utilizing this. But even larger companies, it's hard to get this right. Where there was a certain article that presented there were some hackers or people who were able to exploit the OTA mechanism that was used by Tesla, because they were not signing the firmware packages before deploying them. So you could basically install your custom software into the vehicle. But this was fixed, obviously, when it was brought to attention. But it just shows that it's hard to get right. Another example is from a couple of years back. There was this smart lock, which was commonly used by Airbnb hosts. They had an OTA mechanism as well, but they didn't have a built-in compatibility check. So they deployed the wrong firmware update package to the wrong device and bricked it, rendered it unusable, which complicated it for the users as they were not able to remotely unlock and lock the doors. So these edge cases are typically, when you are developing a homegrown solution, it's hard to cover all the edge cases, so to say. And looking in general of the embedded systems software stack, it's been a very common approach nowadays to use open source components. And if you look at the full stack, typically the product differentiation is at the top. So you have your product specific application that brings value to the customer, or you have a human interface. And the approach is generally trying to utilize open source platforms and components on the lower layers because there's very little differentiation, and that's not where you want to spend your development hours. And this is also what when we designed Mender, our approach was that the OTA solution should be part of these lower layers, and it's not something that needs to be reinvented by every company, and it should be a reusable component together with your operating system and middleware software stacks. And obviously using open source components on these lower layers lowers the development effort, reducing costs, shortens time to market, and you can reallocate development to the important part, which is the differentiation or product differentiation that will bring value to your customers. Mender is the only end-to-end open source over-the-air software manager. So end-to-end means that it's both a management server and a client that you run on your devices. And the obvious benefit is this no vendor lock-in. It's an open source project, so you can use it without relying on external companies. It's under a permissive Apache 2.0 license. And we are strong believers in the open source model of developing a product where we get healthy peer review mechanisms. We have more eyes on the code, which will increase the security, but also the quality of the code. There's also less, by using an open source product, there's less reliance on tribal knowledge. And the typical case in a homegrown solution is there's maybe one person that developed that internal homegrown solution. And should that person leave, there's a knowledge gap on how this solution was developed or maintained. By using an open source project, with a community, you are less relying on this tribal knowledge, and you can utilize a community of people to share knowledge around the product. And that's why we have focused quite a lot on building a community around the product, which we think is very important for it to be successful. We have something we call Mender Hub, which is an online community dedicated to enable over-the-air updates on any device and OS. Integrating a over-the-air solution is in some sense device specific, and that's why we have done over 40 board integrations, reference integrations, so you can get started quickly. And Mender's prime directive is robust and secure over-the-air updates. And these are the core values of the product. On the right-hand side, you can see a quick layout of the Mender architecture, where you have the Mender server running somewhere. It can be an on-premise or a hosted solution in the cloud. And then you have devices connecting to the server to fetch the software updates. I will go through it a bit more later. So looking at the robustness features, we are focused on, it has a built-in rollback support where we utilize a dual AB partition to do software updates. Obviously, the updates are atomic, so it's always installed completely or not at all. There is built-in integrity checks to avoid corruption or things like that. Since we are providing a management server there, we can offer a lot of features around managing devices and the controlled rollout of software updates. I will show a demonstration later on this in more detail on how the management server works and how the different options you have for grouping and for rollout management. Since Mender utilizes the dual AB partition update strategy, there is a minimal downtime while you are doing a software update. That means that the device is operational while the update is installed. And the only downtime you have is to reboot the device to activate the switch between AB. From a security standpoint, obviously the communication between the client and the server is utilizing standard technologies, TLS, so it's encrypted communication. Since we do the solution end-to-end, we can provide, we also provide a device authorization workflow. So just because a device can connect to the server doesn't mean it can get updates. There needs to be a workflow to establish trust before the devices can accept software updates. And this is already built into the solution and can be utilized. And we also support signed images, so you can sign your update artifacts before they are deployed, ensuring that your clients can verify that it's coming from a trusted source. So looking at it a bit more, so it's a singular complete solution. So we are fully integrated from the on-target client to the web-based management server. And I typically also say that we do provide the integration from the bootloader to the server. And you can utilize Mender to update essentially every component in the system. I will go through a bit more later in the later slides of the abilities to update different components and how it works. I am focusing a lot today on over-the-air updates, but Mender does support something that we call standalone deployments. And that's the use case where you are not connecting to a server. So you can utilize Mender in a local environment or updates from a USB stick, for example, which is a common way of updating if you do not have a connectivity. There is an interface to adapt the update flow to application-specific use cases. And this is typically the user application running on your device needs to be in control of the update process. So if you have a human interface, maybe you want to present to the user that there is an update being installed and you want the user to confirm the update and reboot the device to activate it, basically. So there is an interface provided in the Mender client to utilize this. The server architecture is based on microservices, and all the server functionality is exposed to RESTful APIs, meaning it's rather simple to adapt the server to your specific requirements, but it's also easy to integrate with other third-party solutions, such as like CI/CD pipelines and so on. And I will go over a couple of examples later on this as well. But yeah, as the server functionality is fully RESTful API based, it's very easy to extend and integrate into workflows. And generally, we try to keep the system overhead for running a Mender client on your device, trying to keep it as low as possible, and to keep the impact as low as possible if you integrate Mender. And essentially, you are just running a small daemon on your device. The size of this daemon is the only system overhead that we have. We also a solution that can be integrated. We have focused initially on Linux-based embedded system, so it's very easy to integrate with both the Yocto project, Buildroot, Debian. In some cases, we have done OpenVRT as well. So Mender is not an OS provider, but we will instead focus on integrating with existing solutions. I just wanted to cover this dual AB partition update strategy. It has a lot of different names. In some cases, it's called symmetric image updates, but it's also called seamless updates. And this is nothing new. Essentially, it's a pretty common update strategy that's been used in the embedded Linux field. And for example, it's used by Android as well. On the Android phones, they have a similar update strategy. And by using AB partitions, this means that you have a built-in fail-safe and rollback mechanism. And the general idea of this is that you always have it's redundancy. So you have a operating system A, which is the active OS, and that's what's running on your device. When you deploy a software update, you're updating OS B while leaving OS A intact without ever changing any bytes on it or at all. So you're just updating OS B, and to activate the update, you just switch. So now OS A becomes inactive and OS B becomes active. And obviously this has built-in fail-safe and rollback. So if OS B turns out it doesn't really work or it doesn't start, you always have the option to go back to the previous one. The obvious downside of this approach is there is some storage overhead because you need to have a redundant copy of your operating system. Typically nowadays, it's not a huge problem as storage has become quite cheap, and there's room to work with this. But it is the way of achieving true robustness. And doing this type of image-based updates, the downside is also that you deploy quite large images, since you are operating the whole operating system in one go. But there are features like delta updates, which Mender supports, so you can send the binary deltas between images over the network instead of sending the whole image. I'll talk a bit more about this later. So there are also other use cases that are supported by the Mender client, and this is going a bit into technical details, but I hope we can cover this a bit as well. So the Mender client has a built-in updater, which is doing this OS AB image update style of updates. But we also do provide something we call the update module framework, which are extensions to the Mender client. And essentially, the user can implement their own update module, extending the Mender client to their specific needs. And this can be used, for example, to do file updates or application updates. So if you only want to deploy the binaries of your application instead of doing the full image update, that's a possibility by utilizing the update modules. There's also use cases where you can use this to proxy firmware. So if you have a Linux device, you can proxy the firmware to a smaller device that's connected to the Linux device by utilizing Mender and update modules. And I think I wanted to show you a bit. I mentioned a bit about CI/CD pipelines, and this is nothing. It's not a new workflow here that's being shown. It's a typical CI/CD pipeline where you develop version control, build artifacts, test them somehow, and then you deploy them to production. And Mender can be integrated in all of these stages. So Mender can work with when you build your artifacts, you can build what we call the Mender artifact, which is the wrapper around your payload that you want to deploy. And the Mender artifact has all these built-in functionality, such as checksums, compatibility, and signing and verification. The CI/CD pipeline can be integrated with the Mender server, so it can once the build artifacts are completed, they can be automatically uploaded to a test Mender server. And you can, using the APIs, you can actually also schedule a test deployment to a test fleet of devices. And once you're satisfied with the functionality of the software, you can upload the artifacts to the production environment and then roll it out to your production devices. And also looking at it a bit from a developer perspective, Mender can be integrated in a number of other workflows. And the picture I want to paint in this slide is essentially streamlining the workflow from development to production. If you are using the same system, for example, the Mender component, the Mender server, and the Mender standalone modes, you are using the same system during your development, which you are using to deploy to production, which obviously has some benefits, and that you are making sure that it works in your test environment before you deploy it to your devices. And since Mender can be utilized to do standalone updates, meaning that you don't have to involve a server, if you are doing the iterative development on a specific board or device using, for example, using Qt Creator, this can be integrated also to use Mender standalone deployments to transfer the firmware from your PC to your device. But you can also take a shortcut from the developer environment. You can build artifacts and upload them to the test environment and deploy them to a test fleet of devices if needed, before you push the changes you have made to a version control system. So there are a couple of workflows that can be integrated into Mender. And I will be showcasing during my demonstration some of these use cases. I think next is the actual demonstration that I wanted to go through. So I'm going to jump out of this slides. Let's move this. So this is the Mender, the landing page of the management server, where you get an overview of what's going on right now. As you can see, I have 4 accepted devices in my environment, and I don't have any deployments in progress right now. There is a devices tab. So here I can see the devices that I have connected to my environment. So I have 4 devices connected on my local network. The server is actually running on my PC. And these devices are connected to my server. You can expand the device information to inspect them a bit further. There is this concept of device inventory, and this is information that is being pushed by the Mender client to the server. And this is typically static information about your devices. And this can be actually used to do certain deployment actions based on inventory data. So you can see I'm running the boot to Qt for embedded Linux on these devices. There is also, I'm not going to go through too much into it, but there's also a workflow, this authorization workflow that I mentioned. Once a device connects to the server, it's going to end up in a pending state. And it's not going to be allowed to do anything with the server unless it's authorized either by a user, but there is also like a pre-authorization workflows where you can pre-upload identities that you trust, and ensuring that once the device connects, it will be automatically be authorized. There's also some basic grouping. So in my case, for demo purposes, I created a UK and a Germany group with just 1 device in each. But you can create these groups, and then when you do deployments, you can also select deployments based on groups. I will show you a bit more about that later. So here we have the artifacts page or the releases page. And this is where you upload your images that you want to deploy to your devices. These can be further inspected, contain some additional information. In my demo environment, I have not signed these artifacts. That's why we have this red warning sign, but typically you would sign the artifacts and upload them to the server before deployment. There are also different types of artifacts. So this is the root file system update. So, and this is a full image, and you can see the uncompressed size is pretty large. The compressed side is a bit smaller, and this is the size. The compressed side is what's transferred from the server to the client. I mentioned that we do support binary deltas. And in this case, you're still using the AB update workflow, but instead of deploying the full size of the image, you only deploy the binary deltas between two images. So the payload is quite significantly smaller. So these are the number of bytes you need to transfer to the device. And you can further inspect this as well. It contains some additional information. But the major use case for binary deltas is if you have, for example, slow mobile connectivity, transferring 200 megabytes can be quite slow. In that case, you would utilize binary deltas. But it's also some mobile connectivity networks are metered, so you are paying per megabyte. And this can also significantly reduce that by utilizing this feature. And then we have the deployments tab, and this is where you manage, where you can create deployments, but you can also take a look at previous deployments, what has happened, and so on. So you can get an overview of what has happened, if it has failed or so on. So I wanted to quickly show you. I want to create a deployment. So this is a small, a couple of steps you need to go through to create a deployment. First, we want to select the update that we want to deploy. I just need to check what we are currently running released. Okay. Sorry. So we need to select the artifact that we want to deploy. So in this case, I'm going to do a Delta update because I want to be a bit quicker for demo purposes. And these artifacts already have built-in compatibility checks. So this release is compatible with one device type. And then we can select either a group, or in this case, I'm just going to do all devices. And then we get some additional information that 4 devices will be targeted. In the next phase, you set up the rollout schedule. So there are a couple of options. You can start immediately, or you can schedule a start time. And this is primarily for if your device has maintenance windows where it's safe to update, you would typically schedule it during the maintenance window so you don't interrupt the user or functionality of the device. But for demo purposes, we will start immediately. And then you can also select a rollout pattern. So by default, you will update all the devices that are in your deployment. But there are possibilities to phase it out. So for example, we can do 50-50. And in my case, 50% is 2 devices and in 2 different phases. And the use cases for this is specifically if you have a large number of fleet of devices. You typically don't want to roll it out to all of your devices at once, and you want to gradually roll it out. And it's a matter of reducing or managing risk. So typically you maybe start update 1% of my device fleet, wait 1 day, then do 5%, and you will kind of gradually roll it out. And then you have the option to abort if a problem has been discovered during. But for demo purposes, we're just going to do a single phase rollout. And initially, the deployment ends up in a pending state, and now it's waiting for the clients. It's a polling-based mechanism, so the clients will periodically check with the server if there are any staging deployments. And once the clients connect to the server, they will see that there is a pending deployment for these specific devices, and then it will start the actual update. And you can get a real-time overview. As I only have my 4 devices connected to this environment, you can see that they all have noticed that there is an update ready for them, and they have started downloading. And in this case, I'm actually doing a deployment using the Delta updates feature. So they are not actually download the payload, but in this stage, they are patching the images based on what I have deployed. So it can take a couple of seconds before they transition. And soon we will see these devices start transitioning to a reboot state, which means that the update has been, the inactive partition has been updated, and now it's going to try to apply that update by rebooting the devices. I can just wait for a couple of seconds, it should be. And the current running active partition is never, it's not modified or touched. So while it's applying the Delta, it's only working on the inactive partition. And you can see that our devices are switching to a rebooting state, meaning they are rebooted, and now they're going to try to boot this new deployment that I created. And once the default criteria for a successful update is for the Mender client to be able to connect to the server and report its state. And that's considered by default the default success criteria. So once these devices are done configuring network, they will report that they have successfully updated. And it's also possible to extend the default criteria for what's considered a successful update. So you can we provide hooks where you can provide custom sanity checks, ensuring that so you can check if is this process running or is this process connected to this process and so on before you commit to the update. So if you find any problems, you can always say, no, the update is not working, roll back to the previous working state. In this case, they succeeded, and we can see that the deployment has finished and with status successful. And I want to quickly show you a workflow. So I'm going to do, I have these artifacts. Let's clean these up. How this can be integrated in a developer workflow as well. So I've removed these wearable artifacts. So I have a simple Qt Creator project that I created, which is this is an application based on the wait. So I'm just using I'm using this as a reference application for this demo purposes, but we're not going to make any changes to it. So I've just created a project. But what I've added additionally to this environment is that when I do a build, it will automatically generate a Mender artifact and upload it to my Mender server. So if I run a build on this, there is some additional, it's probably hard to see, but there's some additional output after the binary was compiled. And it's running a post-build step to generate a Mender artifact and upload it to the server. And this we can see if we go back to this environment, we can see that it successfully uploaded an artifact. And this one is of type single file because the variable application is a single binary. So it has packaged that into a Mender artifact that now can be used to deploy to devices. Just to show you a bit more in detail what actually happened in the background. So we are simply just running a post-build step in the Qt project, Qt Creator project, where it's running this command. The F flag represents the binary that we want to package, and the minus U represents upload to server. So when we run this, it will automatically upload the artifact to the server. So we should get another artifact uploaded because we did a run through. There's also a possibility to package the application binary if you have a file system image, which can be generated by your build server or something like that. So in this reference example, I can package my application binary into the original file system image, and using the same script, I can run. And this is going to take a couple of more seconds because what's happening right now is that it's injecting the variable binary into the root file system image, and then it's going to create a Mender artifact that is of the type root file system image. So you can deploy your application modifications on something that's valid, so to say. So you are maybe using the latest artifacts from your build server, ensuring that what you are testing is relevant to what you will be deploying later. In a couple of seconds, we should be seeing that this artifact should also end up on the vendor server. So if you go back here, we can now see that we have there's different types of artifacts. They share the name, but you can see this is the single file that we initially created. But now it has also uploaded a root file system image containing the local modified application. And this now we can use to deploy it to a test fleet of devices. I think that concludes my demonstration. So I will go back to my slides. And I just wanted to quickly mention that we do provide consulting services where we can help you out with integrating Mender client with your specific device. And also since the Mender server is highly configurable, we can provide some best practices on how to utilize the Mender server best. We can also provide help with integrating CI/CD pipelines or develop custom update modules for use case specific updates. Yeah, and if you want to learn more, you can we have a documentation, getting started guide. We have the Mender Hub community where we try to, if there's any questions, get involved, just ask anything. We try to be helpful. All the code is on Mender, on GitHub, in the Mender software organization. So we can take a closer look. And that concludes my presentation, and we can take some questions now, I think.
Thank you, Mirza. So then we open the question and answer section of this session. So just a reminder, there is a question and answer box that you can use to post your questions. So please do that if you have any questions to Mirza as well. But let's start with a few questions we have already. So, so are there any different options? So the question is, what are some of the options of running the Mender server?
Mm-hmm. Yeah, it's a great question. So the project Mender is an open source project, meaning that you can run the Mender server on premise or your own cloud provider. We provide a Docker Compose based environment, so it's quite easy to set it up on premise. We do provide a hosted service, meaning that it's a commercial offering where we provide the server as a software as a service, and then you can just point if you don't want to run your own server and maintain your own server, you can connect your devices to our server. So there's definitely flexibility, and you can always change. So if you initially started out with the hosted service, it's always possible to migrate to your on-premise server as well.
Good. Then we also received a question also on the chat, but I think we could do that as well. And I think we can combine them. Perhaps two questions can be combined here. One question is, does Mender support non-Linux devices, for instance, microcontrollers? And that can probably be combined with what are the currently supported operating systems. So basically devices and operating systems supported by Mender.
Mm-hmm. So I can start out with currently supported. So the Mender has initially been focused on Linux devices. So basically that means that Mender can run on anything that's based on Linux. We do provide out-of-the-box integrations. We initially focused on the Yocto project. So we provide our own Yocto layers for integration. There is also integration with the build root. So if you're using build root, it's quite easy to integrate. But we do also provide support for the binary distributions, so such as Debian, Ubuntu. So pretty much anything that's Linux-based is pretty much, there's some kind of reference integration already present. To answer the MCU or microcontrollers, not something that we support out of the box today. It's something that we have started investigating as well. But we actually do have users that have implemented support on their own. Since the Mender server API is fully open and the device-facing APIs are quite limited in numbers, it's fairly easy to re-implement those APIs in your custom microcontroller code to connect them to the Mender server. So it's definitely possible to do it, but not something that we do out of the box yet, but yeah.
Good, I hope that answered the question as well. More practical question here is about what do I need to do to reproduce the Qt demo you showed? Is boot to Qt required, for example?
Yeah, so my demo is based on boot to Qt, where I have integrated meta Mender layers. We can definitely share I can share a link with the participants later on how to reproduce this. So yeah, I'll take a note to follow up on sharing the instructions on how I did the boot to Qt integration and how to replicate it.
Good, and then we're back to more or probably also a theoretical, but also a practical question. So what happens if the network connectivity is lost during an update? I guess that is kind of meant to be.
Mm-hmm. Yeah, so it's a pretty common use case that yeah, you get a network connectivity drop, especially if you, for example, if you are on mobile connectivity and your device is in a moving vehicle, you definitely enter areas where mobile connectivity might be slower or non-existent. But this is well supported in Mender. So basically what happens is that if you are in the process of downloading the update image and you lose connectivity, once you reestablish connectivity, the Mender client will actually resume the download where it was interrupted. And this, of course, helps out without, yeah, it saves both bandwidth, but also, yeah, it saves bandwidth since you are resuming the updates and not starting from the beginning each time.
Good. That actually concludes the list of questions we have received today.
Yeah, I think that is all the questions we had today. But if there are any more questions that we didn't go over, you can send us an email at info@qt.io. But yeah, thank you so much, Mirza and Harald, for your presentation. And thanks everyone for joining. Until next time, goodbye.
Thank you. Bye-bye.
Thank you.